In this lecture, we are going to see the construction rules of how we are supposed to draw the root locus of a system. The first rule is the root locus starts from the open loop pole and terminates either on open loop 0 or infinity. One more small point which you can add in this rule is that the root locus is symmetrical about the real axis. The underlying reason behind this point is that we deal with simple and complex conjugate poles only. Actually, we get symmetrical root locus because we are dealing with real-time domain signals only. If you are thinking hypothetical conditions, then obviously you can draw a root locus which is not symmetrical, but that is not allowed here. Suppose that we are having an imaginary pole 2j, then if we have to convert this signal into time domain, we will get e raised to the power iota multiplied by 2t. If we further try to express it, then we will get cos 2t plus j sin 2t. Even after expansion of exponential term, we will still get a complex time domain signal. But our intention in root locus is very simple, that we are dealing with real time domain signals only. And due to this point, we always get symmetrical root locus. Let's come to the rule number 2. If in the system number of open loop poles is greater than number of open loop zeros, then the number of branches of the root locus will be equal to the number of open loop poles, and the number of branches terminating at zeros will be equal to the number of open loop zeros, and the number of branches which terminate at infinity equal to the number of open loop poles minus the number of open loop zeros. And suppose if the condition is reversed such that the number of open loop zeros is greater than the number of open loop poles, then the number of branches of root locus will be equal to the number of open loop zeros, whereas the number of branches terminating at poles will be equal to the number of open loop poles, and the number of branches terminating at infinity will be equal to number of open loop zeros minus number of open loop poles. The third rule is a point on the real axis lies on the root locus if the number of open loop poles plus zeros to the right side of that particular point is odd. Here, all the poles and zeros, either real or complex conjugate, are counted. Before moving forward to other rules, it will be better if we understand these three rules through an example. Suppose that we are having a system with 2 zeros and 3 poles all lying on the imaginary axis as shown in the figure, and now we are supposed to draw root locus of this particular system. Just for understanding purpose, let me divide the S-plane into 6 regions. The poles and zeros are also numbered. Now consider the portion in the first region. Since there is no pole or zero which lie on the right hand side of the first pole, so the real axis of this region will not be the part of the root locus. Now coming to the second region, any point which lie between the first pole and first zero is having one pole lying on its right side, which is the first pole. Therefore, the region between the first pole and the first zero is part of the root locus. And from rule number 1, we know that the root locus starts from pole and terminates at 0. Now, if we talk about the third region, again, any point lying between the second pole and the first zero is having one pole and one zero. And if we add the number of zeros and number of poles, we will get 2, which is an even number. Therefore, the real axis which is present in the third region is also not a part of the root locus. The same way, you can analyze the fourth region and will conclude that the real axis is actually the part of the root locus, as 2 poles and 1 zero lie on the right hand side of any point lying on the real axis in the fourth region, and 3 is an odd number. Analyzing in the same manner, you can also conclude that in the fifth region also, the real axis will not be the part of the root locus. In the sixth region, the root locus will originate from the pole and will extend towards infinity. And as such, we have also verified the rule number 2, where we have seen that if the number of poles is greater than the number of open loop zeros, then the number of branches of the root locus is equal to the number of open loop poles, which is 3 in this case, and you can see also that there are 3 branches in this root locus. The number of branches terminating at zeros is equal to the number of open loop zeros. This point is also verified. And the last point, the number of branches terminating at infinity is equal to the number of open loop poles minus the number of open loop zeros, which in this case is equal to 3 minus 2 equal to 1. And as such, you can see that there is one branch of the root locus of the system which terminates at infinity. The root locus which is shown on the screen might be looking little bit congested, but you need not to draw all these lines. Let me remove the unnecessary numbers and lines which I draw just to make you understand. The final root locus will look like this. The fourth rule is the branches of the root locus which terminates at infinity move along certain straight lines which are known as asymptotes, whose angles are given by the formula 2q plus 1 multiplied by 180 degree divided by the number of open loop poles minus the number of open loop zeros. The rule number 5 talks about the centroid. Centroid is the point of intersection of asymptotes on the real axis. It may or may not be the part of root locus. The formula of centroid is very simple. We have to subtract the summation of real part of open loop zeros from the summation of real part of open loop poles, the whole being divided by the number of open loop poles minus the number of open loop zeros. These two rules are more like formulas rather than rules. The sixth rule is quite lengthy, but obviously not difficult at all. The breakaway points of the root locus are the solutions of differential of gain parameter k with respect to Laplace variable s, equating this with 0. Theoretically, breakaway points are the points at which multiple roots of the characteristic equation occur. Also, it is not necessary that all the solutions of derivative of gain parameter k with respect to Laplace variable s are valid breakaway points. You have to put the solutions in the original expression of k. If the k comes out to be positive, then the breakaway point is valid, otherwise it is not a valid breakaway point. This rule is very important, and few of you might be thinking that it is little bit complicated, so it will be better if we try to understand this rule through an example. Suppose that we are having system with open loop transfer function equal to k divided by s plus 1 into s plus 3 into s plus 6. Our first step in drawing the root locus is quite simple. All we have to do is simply put all the poles on the s-plane, which are minus 3, minus 1 and minus 6. Now, as I told you before also, our root locus is primarily based on only one equation, which is 1 plus open loop transfer function, equating it with 0. By doing this, you will get k equal to minus s plus 1 into s plus 3 into s plus 6. Now, we have to differentiate this expression of k with respect to Laplace variable s and equating the resultant expression with 0. By doing that, we will get two solutions of Laplace variable s, which will come out to be equal to approximately minus 1.88 and minus 4.78. Even though there is a proper method to check whether the solutions are valid breakaway points or not, but sometimes a little bit of common sense is enough to determine whether the point is a valid breakaway point or not. For example, if we try to mark these points, then you will see the one point is lying between minus 3 and minus 1 and the other point is lying between minus 6 and minus 3. We also know that the breakaway points always lie on the root locus. On the other hand, a centroid may or may not be lying on the root locus. And also we know if the number of open loop poles plus open loop zeros is odd to the right side of any point on the real axis, then that point will lie on the root locus. From that particular rule, you can clearly say that the point which is present between minus 3 and minus 1 is the only valid breakaway point because that point is present on the root locus. However, it is not necessary that you will always get a simple case like this. There may be cases where it is easier to calculate through the formula. Now, if you try to put the value of s in the original expression of k, you will get the value of k to be positive when you put the value of s equal to minus 1.88. Since the value is positive, so the breakaway point is valid. And when you will put the value of s equal to minus 4.78, then you will get the value of k to be negative. And as such, this point will be an invalid breakaway point. The shown root locus is not the complete root locus of the considered system. Few more rules has to be taught to draw the complete root locus. At the end of this lecture, we will see this question once again. Now let's see some general points regarding the breakaway points. The branches of root locus either approach or leave the breakaway points at an angle of plus minus 180 degree divided by n, where n is the number of branches approaching or leaving the breakaway point. Here we are having one more word, which is break-in point. We have breakaway points when there are two adjacent poles lying on the real axis and the real axis between them is the part of the root locus. Similarly, we are having break-in points when we are having two adjacent zeros with the real axis between them being the part of the root locus. The properties of break-in points and breakaway points are more or less the same. The only difference is that root locus splits on the real axis from breakaway points and moves away from the real axis, whereas two root locus branches come from different poles and merges on the real axis at break-in point. The second point is the complex conjugate path for the branches of root locus approaching or leaving a breakaway point is a circle in certain cases only. You may find few problems where the root locus takes the shape of a perfect circle, but that are rare cases. Whenever two adjacently placed poles or zeros lie on the real axis with a section of real axis between them as a part of root locus, then there exists a breakaway point or break-in point between them. Whenever there is a zero on real axis and left side of that zero, if there are no poles or zeros on real axis with the entire section of the real axis to the left side of that zero as a part of root locus, then there exists a break-in point to the left side of that zero. Let's try to understand the last point through an example. The shown graph is the root locus of a system which consists of two complex conjugate poles and one zero. Now read the statement once again. Whenever there is a zero on real axis and left side of that zero, if there are no poles or zeros on the real axis with the entire section of real axis to the left side of the zero as a part of root locus, then there exists a break-in point to the left side of that zero. I hope from the shown example, the last statement is crystal clear to you. Now let's come to the next rule, which is the point of intersection of root local branches with the imaginary axis can be determined by using the Routh-Hurwitz criteria. The roots of auxiliary equation will give the points of intersection of root locus with imaginary axis. The last rule is the angle of departure is obtained when the complex pole terminates at infinity. The angle of departure is tangent to the root locus at the complex pole. The angle of departure from an open loop pole is given by 180 degree plus the net contribution of angle from all the other open loop poles and zeros. Let us take another example so that you can understand what is actually the angle of departure. As you can see, we are having two complex poles which are actually conjugate pole pair. Now, the angle of departure is the angle at which the root locus departs the complex pole. This angle is obviously measured from the real axis. Phi is representing the net angle contribution at any pole because of all other open loop poles and zeros. Remember that root locus have different angle of departures for different poles. Similarly, we are having angle of arrival which is obtained when pole terminates at complex zero. The angle of arrival is tangent to the root locus at the complex zero. The angle of arrival at an open loop complex zero is given by 180 degree minus the net angle contribution at any pole because of all other open loop poles and zeros. There is one more point which is not used frequently, but if any out of the box question comes, then probably it might be useful. The value of k for a particular root location can be obtained from actually drawn root locus plot by substituting product of phasor lengths from the point to all the open loop poles divided by product of phasor lengths from that point to all open loop zeros. For the above formula, it is very important that the same scale is employed for both the real and imaginary axis of the root locus. Now, let us try to solve a very simple question where we have to simply find the angle of departure from the complex poles. We already know the formula for angle of departure is equal to 180 degree plus the net angle contribution from all the other open loop poles and zeros. First, we will consider the complex pole minus 2, 3j. Our first step will be to find net angle contribution from all other open loop poles and zeros. For that, I have drawn 3 dashed lines which are joining the complex pole minus 2, 3j with all the other open loop poles. The angle which these 3 lines make with the positive real axis are the net angle contributions, which are represented as phi p1, phi p2 and phi p3 are actually the angle contributions caused by the other poles, the summation of which is simply net angle contribution by all the other open loop poles to the reference pole minus 2, 3j. There can be different ways of finding the angles, but I think the simplest is obviously to find the slope of different lines. You will get phi p1 equal to 180 degree minus tan inverse of 3 by 2. Similarly, phi p2 will be equal to tan inverse of 3 by 4 and phi p3 is equal to 90 degree. Now, all we have to do is to put all these values in the formula of angle of departure, and by doing that, you will get the angle of departure for the complex pole minus 2, 3j is approximately equal to minus 70.46 degree. In the same manner, you can also find the angle of departure for the complex pole minus 2, minus 3j, which will come out to be equal to approximately 70.46 degree. However, from the first rule of symmetry, you can easily determine that the angle of departure from the complex pole minus 2, minus 3j will be equal to 70.46 degree. Now let us see the same question which we discussed but had not completed its solution. We got two values of breakaway points and have also determined that minus 1.88 is the valid breakaway point. Now our next step should be to find the value of angles of the asymptotes and the value of centroid, which after putting the value of different parameters in the formula, we will get the angle of asymptotes to be equal to 60 degree, 180 degree and 300 degree. Similarly, the centroid will come out to be equal to minus 10 by 3. We plotted a point on the real axis minus 10 by 3, which is the centroid of the root locus, and has drawn two dashed lines at plus minus 60 degree from the real axis. The third asymptote is actually coinciding with the real axis. One more point from the rule regarding the breakaway point is that the branches of root locus either approach or leave the breakaway point at an angle of plus minus 180 degree divided by n, where n is the number of branches approaching or leaving the breakaway points. By using this point, we will get that from the breakaway point, the two branches split and moves away from the real axis after making exactly 90 degree from the real axis. So finally, our root locus will look like this. I hope you have enjoyed this lecture.